In the last video, we saw how to find the linear combination of individual matrices representing images of individual threads, which could potentially yield a matrix that represented the string art of the input image. Unfortunately, the method we derived turned out to be totally useless because the coefficients of this linear combination could potentially be fractions or worse, negative numbers, and therefore cannot be used to make choices of thread vectors necessary for the portrait. The pseudo-inverse method works well in an environment where there are no constraints on these coefficients, but our situation does in fact dictate two specific constraints. One, these coefficients have to be whole numbers because we could either choose to include a given string or choose not to. We can't have half a string or 0.4 of a string. And two, the solution must present itself in a way that we get an ordered set of nails starting at a random choice of nail so that we can string the whole portrait using a single piece of thread without cutting it at any point. Even though we cannot use the pseudo-inverse technique, we can use its underlying concept, which is to minimize the error between the input image and the output string portrait to achieve our goal. For example, let's say we have n nails on the canvas and we start at nail 0. From here, we could choose any of the remaining n-1 nails to draw a string. We shall make that choice in such a way that the one string we choose out of these n-1 strings shall reduce the difference between the input image and the output by the largest possible magnitude. We repeat this process again and again for each string until we cannot reduce the difference any further, and by then we should, in all probability, have the string portrait ready. Let me just make a copy of the previous program and we shall use it as a starting point for what comes next. I'll also throw these old files into an archive which we can access at a later stage should the need arise. Let's fire up our text editor, and to quickly recap, this is the program we wrote 2 videos prior, and this basically generates the image of all possible strings on a blank canvas of the same size as the input image. To modify this to suit our needs, let us begin by reading the input image and converting it to grayscale. Here we have gathered the input image dimensions, and let's allocate an array to hold the grayscale image data. After that, we will iterate through the file's image data section to collect the image data. Remember, each pixel is made of 4 channels, 3 colors and 1 transparency channel, and we shall take a weighted average of the 3 colors as we discussed in the first video and save it into the array we just allocated. With this, we have the array populated with the grayscale image data. Let's update these comments and make sure we free up the memory and all. We can skip the cleanup because our dynamic memory is gonna go back to the OS at program exit, but hey, whatever. Now this is the code section responsible for rendering the strings which we saw before, and also the section which we have to replace with new code that makes the string portrait. Let's quickly review what's going on from the beginning. We open the image file, collect the image pixel offset and image metadata and store it in memory, and then get the image dimensions. We use the image dimensions to allocate memory for the grayscale array and read the image data from the file. Convert each pixel to grayscale and store it inside the array. Oh, and I almost forgot, we have to seek to the point in the image file where image data starts before we read the data. Otherwise, we would be reading garbage values. So let's fix that. There we go. Next up, we allocate memory for the working pixel array. That is the one which we use in each iteration to store the thread image data, and the thread accumulation array, which will accrue the images as we develop the string art. Finally, we crop the image in a circle and we'll be done. Let's write a function to generate the string art. As inputs, let's see, it would need the grayscale image, the working array, and the accumulation array and their sizes. Let's put this function down below here. So this function takes in the grayscale image as the input and populates the accumulation array with the string art, or at least that's what I'm planning to do. Inside our function, I'm going to start by declaring a variable to denote the starting nail from which I'm going to start stringing. Let's call it the start nail, and I'm going to set it to 0. We are going to start at nail 0. You could start at any nail and it really doesn't affect the final outcome that much. Just make sure this number doesn't cross the max nail count on your board. Speaking of which, let's declare a macro to specify the maximum number of nails on the canvas. I'm gonna call it max nail count and set it to 200 for now so that we have 200 nails on our board. We can change it later if we want to. Next up, we are going to start a loop, and inside this loop, we will write code that selects one string at each iteration. The idea is to run the loop until a certain condition is met, by which time we have a reasonably good string portrait of input image. For starters, I'm going to define the stop criteria as to depend on the maximum number of loops we are going to string the thread across these nails. Let's define this max loop count to be 600 for the time being. What that means is that if I start at nail 0 and go to nail 32, that's one loop. Next, if I'm going to go from nail 32 to 87, that's the second loop. So on and so forth until we hit 600 such loops, at which point I'm going to say enough is enough and break out of the loop. To keep track of these loops, let's have a counter and have it compared to the max loop count. Do not forget to increment the counter inside the loop, lest we want this program to hang without outputting anything. Now inside the loop, we are going to have to make a single choice amongst many possible strings that could be strung from the start nail. For that, we have to try out each string and choose the one that minimizes the error between the portrait under progress and the input image. This warrants a second loop inside which we shall generate these threads from the start nail. But before we do that, we need to define a variable to keep track of the ending nail, which initially starts out as the next nail to our first one and progresses from there. Inside the second loop, we shall generate the thread and calculate the error between our string portrait and the input image. For that, I'm going to write another function which specializes in calculating this error. Obviously, it would require the input image, the thread we just generated, the accumulation array, and the array size as inputs. I'm going to require this function to return the error as a double precision floating integer. Now that we have got the error, what do we compare it against? For that, we should have calculated the initial error for the first thread before diving into the second loop. I'm gonna do that here before the inner loop starts, and let's call it the initial error. What happens now inside the second loop is that as soon as we calculate the error for any given thread, we are gonna compare it to the initial error, and if it is smaller, we are gonna note the ending nail which generated the smaller error. Let's call it the optimal end nail. We shall also update the initial error to this newer and smaller error value so that if we find more nails that generate even smaller errors in the future, we are able to trap them. And when we are done with the loop, we have the minimum error stored in the initial error variable and the corresponding end nail which generated it in the optimal end nail variable. We'd want to increment the end nail variable after this and make sure it rolls over if it were to hit the last nail. For example, if there are 50 nails on the board and you want to roll over after 49, you would want to go to nail number 0 and not 50. To do that, we just modulo the incremented value by the maximum number of nails. In fact, I want this at the beginning of the loop because we would have generated the initial thread already. We would also want a nail counter to make sure we just run through the max number of nails after which we jump out of the loop. I'm going to declare it here in the beginning inside the first loop, and we would want to immediately increment it after we try the first thread and after each subsequent thread inside the second loop. We want the loop to run the maximum nails minus one time because we have already made one thread up here and want to compensate for it. Finally, once we are out of the second loop, we want to get that optimal thread and put it inside the accumulation array. For that, we would have to generate the thread again, which is not very optimal, but we shall try to optimize this whole thing later. Once we are done, make sure we prep the loop for the next iteration by setting the start nail for the next iteration as the current iteration's ending nail. We must also take care to ensure the end nail rolls over if it hits the last nail number, like I said a while ago. Let me also add this diagnostic message which tells us how we are jumping amongst these nails. Now let's shift our focus to the error calculation function. This is the core component of our algorithm. So what is this supposed to do? Remember, when we say error, we are talking about the numerical difference between what is and what ought to be. In our case, this would be the numerical difference between the input image and the string portrait in progress. So we would want to take the thread we just generated, add it to the accumulation array, and then find the difference between the accumulation array and the input image, the grayscale image. We are basically asking this. If I add this thread going from nail A to nail B to my ongoing portrait and then find the difference between that and the input image, how big is it gonna be? It's that simple. So here we start a loop to go over the arrays. Inside it, first we add the corresponding pixel of the working array to that of the accumulation array. I have talked about how to do that in detail in part 4 of this series, and in that I've explained how adding pixels of one image to another works in the context of superimposing threads on top of each other. I highly recommend you take a look at that once if you are not able to follow what's going on in here. Once we have added these two pixels together, it's just a matter of taking the difference between this sum and the corresponding pixel of the input array and accumulating this over all pixels. I'm going to call it the aggregate error or the difference between the input image and the thread we just generated, and we return that value. I want you to realize that this is one way of defining this so-called error. If you can come up with a better definition, all power to you. So that's the basic algorithm, and let's try it out. Let's compile it, and oops, there's an error. Let me see. I got the wrong name here. Okay, let's try that again. And yeah, all right. Let's run the program on my cat's picture. It looks like the program is running all right, but the speed of execution is not to my liking. And that is because of all that redundant thread rendering we are doing inside that loop, which is hell a lot inefficient, that our DS and algo guys would probably be pulling their hairs out for. But we should worry about that later. Let's first see if our program is even correct. It looks like we are generating an ordered list of nails perfectly, and error also seems to be going down in each iteration. So it looks like everything is all right. I'll speed this up and let's look at the result. Would you look at that? Look at that. Can you believe those are just straight lines? Anyway, a couple of things here. This could, of course, be improved by a lot. For starters, we could just add more nails on the board. Right now we have 200 nails on the board and we could try with 300. I did that, and here's the result, and it actually looks worse than the previous attempt. We can keep going, but there are other ways of improving this. In the next video, we shall look at one such method which could potentially make this converge faster, and also try to optimize the algorithm for speed by eliminating redundant thread generation that's happening a lot in our loops. I'm finding it difficult to find time to make these videos, so it might be a very long time before I release the next video. In the meantime, I encourage you to go ahead and make your own optimizations and improvements to this. The basic structure of this algorithm is what you just saw and probably wouldn't change much under any future improvements. Most of what I set out to tell you has been said, and I'm gonna take it easy from now. As always, the code is in GitHub, the link for which is in the description.